this is something I've been wanting to go over for a couple of days now, and I kept putting it aside because we were um, basically one thing led to another, and I'm glad that yesterday the class went the direction it went because it gave me more of an opportunity to show you a little bit more about the machine. And what I said, Greg and James, you guys just came in, was I really liked the fact that you guys were watching that one video and were able to identify that this guy was calling parts by the wrong name. It means that you're starting to learn and recognize the description and the location of the parts on this machine. Now, we mainly been talking about a Whirlpool machine, so my thought process for tomorrow's assignment was I might find some pictures of some other machines and see if you can compare where the thermal cutoff or where the high limit thermostat would be on a GE machine or be on a Frigidaire machine that's open. Like, the manufacturer doesn't always put all the parts in the same place. So I really want you to like try to figure it out. Some of them you can look at parts breakdowns. You can search the internet to try to get some of this information. Remember, I showed you Sears Parts Direct and the Frigidaire B2B site, and they had like a parts breakdown of all the parts on the machine. Thank you. All the parts on the machine. So I want you guys to try to research it and try to figure out. So one day if you run across a machine you've never seen before, you can say, oh yeah, that's just the high limit thermostat. That's the operating thermostat because of this. So that is sort of like what I want you guys to work towards. Not just this Whirlpool dryer, but other brand dryers, the same components. Because all dryers have a heating element, except for the gas ones, have a heating element. They have thermostat. They have a safety thermostat. Some have thermal cutoffs. They all have timer switches. They all have push-to-start switches. So if I can find the schematic to go with a specific machine, I will give both. But I want you to try to identify which part is which on there. So the idea behind here is we're going to start at L1 here on the diagram, and then on the left-hand side, I actually put two different pictures together. This is a different picture of a control panel. It almost looks like it's part of the same picture, but it's a different control panel on top of a dryer because it shows all the parts. And what I want to do is I want to trace the circuit that are going through not just the heating element. Let's see if we could maybe do some of the other components as well. I'm going to switch to the black marker for the black line here. So this point right here on the diagram where it says L1, where physically on the machine would you find that?
Where those three prongs are, where you plug the cord in?
In this area right here?
Yeah, that one right there.
Now, which one of them would it be?
The first one?
Well, left to right.
The left side.
Yeah,
The
the
left.
first one on the left. So the black one would be here, right?
Yeah.
Now, that black line comes in and goes to what? What does it go to right here?
Timer switch.
It goes to a timer switch, and where would I find that on the machine?
It's up in the control area.
Yeah, on the top panel.
Okay, well, all these parts are in the top panel. Let's just say one,
On the right.
2, or 3. Which one of them would it go to?
3?
It'll go to 3, correct. So that black wire is running up here through this harness here, and it's connecting to the timer right here. I don't know if you can see that too well. Let me just go over it with a yellow, just so it appears a little better. I tried to follow the color code, but that's not going to happen. So that's this line right here. Now we go through the timer. We come out the timer with a red wire. Where does it go to?
Thermal cutoff.
Okay, so where is that? I mean, obviously they got the name there, but it's right here, right?
Yeah.
So there'd be another wire coming off this timer running back through this harness, run behind that screw, and it would probably be this top wire right here coming into the thermal cutoff. Now I'm going to explain the importance of this, but again, what we're trying to do now is we're trying to take the diagram with a bunch of straight lines and see how is it actually flowing through the machine. If you guys have any questions, stop me and say, wait a minute, you know, wait a minute, what are you doing there?
Wait a
Okay?
minute, what are you doing there?
I'm just messing with your head. This isn't even a dryer. This is a stove.
Stop it.
All right, so from that thermal cutoff, where do we go now?
Wait, no, I had a question, seriously.
Okay, go ahead.
The yellow line that you just drew from which is really like a red line, right?
Yes.
From the timer switch back to the thermal cutoff. Can you highlight that on the diagram?
I just did. It's right here. You see it?
Okay.
So
Yeah,
it's coming from the timer, going to the thermal cutoff. So that's this wire right here. And I tell you what, I'm going to put A. That's not a very good A, but that's A here. And I'm going to put B here for the wire. Like, I'll put a letter for each wire. And B here. So you can look at the wire and see the wire here. Does that help?
Got it. Yep.
Okay. So the next wire coming from the thermal cutoff is this bottom one right here. Where should I go with that? That's this wire right here. Where's it going to?
Operating thermostat.
Okay, where would I find the operating thermostat on this machine?
The bottom left of the
Yeah, under the thermal fuse.
Yeah, it's right underneath the thermal fuse. So that wire is going to go back into the harness, run down, and it's actually that thick one right there coming straight down. And there's a red one right here, and it's running right into the thermostat. So that'll be C. And this wire right here is C. Are you guys starting to see how it's pieced together and how the diagram is going? Just a little bit?
yes.
Mm-hmm.
Okay, so coming out of that thermostat, where are we going to go? We're right here now on HT3.
To the high limit.
Okay, where's that at?
It's on the right side.
Okay,
At the bottom of the heater.
Yeah.
Well, actually, it's on top of the heating element terminals, but it's towards the bottom of the heater box. So this one right here comes up, and there's a little red wire, like right above that yellow line. It jumps down, if you can see it, and it comes into the high limit thermostat there. So that would be this wire here, and that'll be D. So that'd be this wire here, D. That's a horrible D. Let me redo that.
What you mean? FMFT or something?
The sleepy time one.
Okay, so from the high limit, it goes to, that'd be E. It goes to what? The heating element. That's the heater there. That would be right below it. So there'd be another wire here going there. That would be E.
It'd be like a jumper, no?
Sometimes they're connected directly to it. If we look at the previous slides that I had, can you see this one has a wire right here connecting to the element directly?
Okay.
So that's the high. Now some of them, they don't have a piece of wire. That there's just a piece of metal on this thermostat, and it just connects directly to it without wire. It's just metal against metal.
Okay.
Okay? So let's go back to this diagram here. So where do we go from here?
To the
To that switch right there.
To what? What is
To that
that?
switch right there.
centrifugal.
Yeah, but where would I find that physically in the machine?
Oh, on the motor.
On the motor. And that's on the other side of what panel? What's the name of that panel?
Bulkhead.
The blockhead.
The bulkhead. The bulkhead. Bulkhead. All right, so that would be F. And so that goes to the bulkhead. Now, if I follow that wire right there, it goes down and goes to the motor. And that would be F right there. The wire goes underneath the bulkhead and connects to the other side to the motor, F. Then what do we do here?
Back up to that power cord.
Okay, I'm going to use a different color. Where on this power cord would I go to?
The right side.
The far right screw. That would be
Yeah.
line 2. So there'd be another wire coming up, and I'm using just the red wire just to... It would run up here and would connect to that. Now that's a spaghetti mess, isn't it?
Yes.
So the diagrams are drawn with straight lines. These are called schematic diagrams. Schematic and pictorial. Let's just do a brief thing of a schematic versus a pictorial diagram, just so you guys know what they are. You have... I guess my caps lock was on, didn't know it. Okay, so we got a pictorial and a schematic diagram. Now, when diagrams were first made for machines and everything else, people were just drawing how they see it. So if I was to draw a pictorial diagram of a lamp, okay, and the only reason why I'm saying is because it's easier to do that, you would look at a diagram like this. Let me... You'd have a plug, 2 prongs, and then you'd have a wire coming off of the plug, and it would go to a switch, and depending on what type of switch it is, and then coming off the switch, it's going to go to a light bulb. And then it's going to return back to that lamp. Now that's all good, but if I asked every one of you without seeing my drawing first, asked you to draw the wiring diagram for a lamp and use pictures, do you think that everybody's diagram would look the same?
No. Not at all.
No, and some people can draw and some people just can't. So it would be a total mess for those who can't draw. So they said we got to come up with something that's more organized or more laid out, that it would be easier for one who's wiring it to read it, but then it's harder to compare it because you guys can see the plug, you can see the switch, and you can see the light immediately. If I never even told you it was a switch and a light, except for you can't really read the word off down there that I wrote, you can almost tell what those parts are. You would recognize them because you'd identify with the picture of it. But the same drawing as a schematic, the power cord could be one of 2 ways, and most of the time we draw them like this. We put an arrow, meaning line 1, and we'll put L1 here. We'll go to a switch, a light bulb, and here neutral. Now, which one was faster for me to draw?
Second is schematic.
Yes. Now, code-wise, if you notice, the control is located on which line? Neutral or line 1?
Line 1.
1.
Why do you think they do that?
Why? I guess that's where the current's coming directly from, huh?
Yeah, well, believe it or not, AC voltage comes from, 2 different directions. But why do you think specifically on line 1? I just added this to the screen here because it's going to come up to the next thing I want to talk about. Well, line 1, like you said, is where the current or the power comes from. And the important thing is that if you're unscrewing the light bulb from the lamp and the light bulb glass breaks in your hand and you touch that filament right here in the bulb, if the switch was on the other side, there would be power here all the way through the bulb up to the switch. And someone could get electrocuted or hurt if they had the switch on the neutral side. If you put the switch on the neutral side, you'll turn the light on and off, but the voltage would already be at the bulb. And in this case, the electricity stops here, so if you unscrew the bulb and it breaks in your hand, you have very little or no risk of getting shocked as long as the outlet here is wired properly.
Ah.
Okay, so when you look at wiring diagrams, and if we go back to this other diagram real quick, if you look, most of the switches and controls are on the line 1 side, coming into the motor, up here. This one's after the timer, but that's because it does something different with the timer, makes the timer work differently. But all these controls are on the line 1 side. We do put something on the line 2 side because line 1 and line 2 are basically the same in electrical voltage. They're just different phases, and I really don't want to get into that too much, but different phases, when they're put together, they add the voltage up. Okay? So by putting a switch on this side, we prevent line 2 from coming to the heater as well. Okay?
Got it.
Let's go back to this here. Look at this as an electrical outlet that you have in the wall. One of these terminals is line 1. One of these terminals are neutral. And one of these terminals are ground. Which one of the 3 is line 1?
The left one.
Left.
The bigger one.
No.
No?
Line 1 is the small one.
Okay.
The bigger one is actually neutral. So it's backwards from what we look at it on the diagram, isn't it?
So you tricked us.
I didn't trick you. That's the way diagrams are drawn, and that's the way your outlet is wired. Now, the third one is what, guys?
Ground.
Ground. Okay. Now, if you look at this screw, and I don't know if the picture's good enough for you to see it. Can you see a difference between those screws on either side?
Yeah, they're different colors for sure.
Okay, the one on the right is color what?
Bronze. Well, I guess copper? I don't know.
It's like a brass or a copper color.
Yeah.
Let's just say gold.
Okay.
And then the one on the left is what?
Silver.
Silver. That is on purpose. That is so you know what each wire goes to which screw. And then this one down here is green, isn't it?
Yeah.
That's the ground. So this one actually connects to the ground here, and it connects to that ground. Okay? So line 1 would come in here, and on the side of these outlets there's a piece of metal, and I want to show that to you real quick. Let me see if I can find a picture of the side of an outlet. But those outlets can be wired different ways, and I'm trying. Okay, I think I found it. Give me a second here. If you look at this outlet, and I'm gonna lay it over top of the diagram that we just did. Let me make it smaller just to compare. I'm gonna erase this diagram. Now, if you look here, we have the small one on the right, the large one on the left, and the ground plug here. Why do you think they make one smaller and one larger?
It's not polarity, right?
It is polarity, but is there
So
a
you can't make
reason?
a mistake and put the cord in wrong, the plug in wrong.
Yeah, because if it's a three-prong plug that has the ground on it, like hold on a second, because I have everything. This is why I want these multiple monitors. If it's a three-prong plug, the ground only lets you put it in one way. You cannot plug it
Yeah.
into that outlet any other way.
Oh,
But, and let me just put this on the side here. But if it's that it has the plug, but it doesn't show it. If it's a two-prong plug, like on the end of a drill, it has only two flat blades. So by making one larger and one smaller, you can't flip it upside down. Okay? Now, the thing is that if you flip it upside down, the drill's going to work just the same because it's AC voltage and it does not change the way the drill motor goes. But what happens is the power's backwards. It'll still work normal, but safety-wise, it will not be safe. That it could harm you because there's voltage at the motor all the time. Now, what I wanted to get to real quick, and then I'll get back to the dryer, was here's these two screws on this side. They're silver, but if you see this piece of metal here, it's connected with a piece of metal here to the other outlet. So you could put one, I'm sorry. See, this is the problem with my video now, saying I don't have enough colors. Okay, so if I put neutral here, because of this metal piece, this is also neutral. And the same thing with line 1. If I put line 1 to the top screw, it's going to feed the top outlet, but there's a piece of metal to this one feeding the bottom outlet as well. But do any of you guys have any outlets in your house where one of these two is controlled by a switch on a wall? Like if you walk into a living room, you can turn the light on and off, but the other one is not?
yes.
Okay, does
It's
anybody
just
know?
wired differently.
Or do you know how that's wired?
It doesn't have that little that metal piece you're talking about.
That metal piece is broken, but I'm only going to break this one on this side because I'll put one neutral here, and because of the metal, it connects here. So these two are sharing the same neutral. But the two screws on this side, I'll break this piece off, and this one here I'll put to a light switch on a wall, you know, by your door in your living room or something. And then I'll go to line 1 at the circuit breaker panel. But the bottom one has a different line 1 all the time with no switch. So whatever you plug in here is going to work right away. But this one will not work until you turn the switch on the wall. If you don't break this, it's not going to work that way. Any questions on that?
Now, isn't there? Okay, so you know how like GFIs?
Yes, sir.
You could wire it so that you could have, like on a circuit, you could have one GFI and two other receptacles, and that one GFI will kind of make those other receptacles like quote unquote GFI. You know what I mean?
Yes, and that's very good. So what happens is, let me get a GFI outlet so some people understand. Not everybody knows what you mean by GFI. Do you know what the GFI stands for?
Ground fault interrupter, right?
Yeah, ground fault circuit interrupter. And those are used in what we call wet locations. And what happens is, let me just type this in real quick because it's hard for me to talk and type at the same time. I'm just not that ambidextrous or whatever you want to call it. So let me explain what happens here in a GFI break outlet. I'm just going to grab one real quick to show you. I can't grab that. I can't grab it from that picture. I got to grab another one. Hold on. going to Google and finding an image and then trying to bring it into this software. Sometimes it's just by dragging, and sometimes it just don't work. Okay, so you could have one of these GFI, and if you guys have any in your house, especially newer construction homes, you're going to find this in your kitchen, your bathroom, your laundry room, maybe even on a balcony or patio or something, especially places where there's water. You know, we have a ground, but if there's a slightest electrical, let's say, ground or fault, it's going to trip this little button like a circuit breaker, and then all these other outlets are going to be without power. So how do they do that? So we got neutral on this side. We got ground here, just like a regular outlet. But we have line 1 coming into the upper screw. And on the outlet, you have to read it because one is line coming in, and the other one is actually line, and I'm going to call it line in.
And line out.
Yeah, and the other ones are out. And so what this would do is this would run to this outlet and then piggyback over to the next outlet like this, and all the neutrals are still connected the same way. So if this pops, the power can't go through here and feed the other outlets in that same circuit. Does that make sense? What do they call that? How are these outlets wired to the first outlet? We would call them wired how? They are wired in
Series.
In series, correct. Series means one after the other, so that power has to come in this one, and then it goes out this to these two. Now, these two don't have to be in series with each other, but they do have to be in series with the first one.
It's like old Christmas lights.
Yeah, well, I do a little bit of electrical switches and stuff like that because I try to get people to think about circuits. Have you ever been in a hallway or a stairways and there's a switch at the bottom of the stairs and a switch at the top of the stairs that control the same light?
Yeah.
Yes.
And you turn the switch at the bottom of the stairs on so the light comes on. When you get to the top, it turns the light off. Maybe one of the assignments would be for you to figure out how is that wired, and I want you to draw me a schematic for that.
What's the other term? The opposite of in series, where it's like
Parallel.
Yeah. You have series, you have parallel, and then you have what they call series parallel. Like these two are parallel to each other because this wire goes in here, but this one is also connected there, but it doesn't depend on this one to be working. If this outlet was bad, this one would still operate. So these two are parallel to each other. But you see how power comes in here and comes out to feed those two? So those two are in series with this one. There goes series parallel circuit.
okay.
All right, now let's go back to the dryer and its circuit. You know what? Let me grab my meter leads. I have to copy them one at a time. Hold on. Copy. Paste. What the heck? I don't know why it keeps going there. It's like, I don't know, it won't allow me to connect. Control C. Control V. There we go. It brought my meter. Let me get the red one. Alright, so remember the guy that was doing the troubleshooting of the dryer? He was testing the components how? What type of test?
Ohms.
Yes.
Ohms.
He was doing an ohms test. Now, the other test would be a voltage test. Okay? I'm going to tell you my preference is that we test with voltage. It is not the safest thing, but if you use alligator clips, unplug the machine, connect your meter leads, then plug the machine back in, you're not holding them and not susceptible to electrocuting yourself. You could do that. But let's talk about the test here, because I want to explain what is the difference between an ohms test and a voltage test and why you would do either one of them. Now, if I was doing an ohms test right here, what was the reading the guy got in that video? Do you remember?
10.
Okay, that's close enough. He had like 9 something, so let's just say 10 ohms. What is he testing right there?
What is he
The
testing?
resistance
The
of
resistance
the
of what?
component.
The
Of
resistance
the component.
but what component is it?
Oh, the heater.
Okay,
In
so
this
he's
case.
checking the resistance of the heater. Man, I'm writing in it for some reason that it's almost like the pen's out of ink. I don't know why it's giving me that. When I'm writing, I have something similar to a tablet and almost like a pen in my hand. That's what I have the ability to write. Okay, so testing ohms, I'm testing from the red to the back meter lead right here. But where is that on the machine?
It's E.
It's E and what other letter?
F.
E and F. So F is this bottom wire here. So I'm going to put this red meter lead here, just like it would be on the diagram. And I'm going to take the black meter lead and put it here. It's hard to see, but it's right underneath that thermostat. So that's the same 2 points, and I can check the heater there. Now, I can also do a voltage test at that same point. I'm going to put my meter leads back on the diagram for a second now, because I want you to see something. First of all, how much voltage should I have at that point?
There?
Yes.
At the heater?
Yes.
You should have what? 240, no?
Yeah, the diagram up here says 240, so line 1 is here. And this little line here, by the way, guys, is not a wire. It's not an electrical circuit. They're just saying from this dot to this dot way over here, I have 240 volts. Okay? So this is not a wire. And neither is this one down below.
Okay.
I just want you guys to see that because I don't want you to get confused. But line 1 comes all the way to E, and line 2 comes all the way to F here. You see that? And I should have 240 volts. Now, just so you know, transformers in homes don't always do the same. Sometimes you'll get 220, 208. If it's between like 215 and 240, the heater is going to work. The only difference is at 240, the heater is going to get hotter faster. Okay? So sometimes you say, well, I don't have 240, I have 220. The heater will still operate. It just won't operate as hot. Okay? So I'm going to do a voltage test. And the voltage test should be 240 volts. Now my question is, I'm testing for 240 here. Am I testing the heating element?
Yeah.
Anybody else?
Wait, hold on. This is based on the meter leads in the schematic.
My meter leads where they are.
Yeah.
I'm getting a reading of 240 volts AC. That's the same as putting the meter leads here and here. Okay?
Mm-hmm.
Am I testing the heating element?
Yes.
No.
You're testing this.
You're testing the line.
Okay? I'm testing the circuit. Carl, you're right about the line. But when I put my meter here for voltage, I'm seeing if the voltage is coming from the plug to my element. So in ohms, I'm checking between the two meter leads, and I'm using a battery in the meter to give me a reading. So the battery is pushing through one meter lead and coming out the other one, and I'm getting a reading on my meter. Whether it's an analog needle or a digital meter, that's how it works. The machine must be unplugged when we do that because it will burn my meter up. Now when we're doing voltage, it's the electricity in the circuit that makes the meter give me a reading. If there's no voltage, I won't get no reading. I do not use the battery in the meter for that. And the voltage is coming from L2 up here and L1 here. So the voltage is coming from the plug and it's coming down to the element here. And the voltage is coming from this plug to the element here. So I'm testing the circuit to see if I have electricity. Now, here's where it gets a little tricky just because of the verbiage. If I have 240 volts at that point where my meter lead is, I have 240 volts here, and I'm just going to redraw my F a little bit. I erased it by mistake. If I have 240 volts here and here, the dryer is running and not heating. What is the next step? What do we do at this point? We know the dryer's working. We see the drum turning. There's no hot air coming out. We go to the element and we say, do we have 240 volts? And the meter says, yeah, you got 240 volts. What does that mean?
I mean, you got power for sure.
You need to identify the circuit and isolate each of the elements.
Not actually, because I'm at the heating element, and how much voltage does it take to make that heater work?
240?
240. And my meter says I have 240, and my heater's not working.
Oh, it could be how the dryer is wired.
The heater's bad.
Oh, okay.
If we went, I don't know where I drew that lamp, I erased it. But if we went to the lamp and the lamp didn't work, even if you didn't put a meter on it, what would be the first thing you do? Check to make sure it's plugged in. Okay? It's plugged in. Next thing you do is go get another bulb and see, put a bulb in here and see if it lights up. But the thing is in a machine, we have more than just one switch that turns it on and off. And these components are not as easy to get to. Plus, you don't have every part on your truck for every part inside this machine. So you can't just be putting a part on and say, no, that didn't fix it. No, that didn't fix it. So voltage to the component or to the load, and the load is not operating, you are done testing. The load is the fault. So if you have 240 volts to the load, and the load is not working, the load is bad. That's just plain everything. If I got power to this motor, how much power does this motor have, the dryer motor? If you look, line 1 is here. And if we go off the other side of the motor, it goes to what?
It's 120.
To 120. So if I have 120 here and my motor doesn't run, I change the motor. Having voltage to the load is telling me that all of my controls and the wires connecting them are all good, because if any one of them were to fail, I would not have voltage at my load. For example, if this switch was open, would I have voltage here?
No.
No.
No. So we do something when we're troubleshooting machines, and I know that I'm going way advanced here, so I just want to see how many of you can actually follow this concept. Okay? I'm going to take my black meter lead and stick it back here on the heating element. I'm going to take my red meter lead and I'm going to stick it here on my heating element. Right? Now, I'm just going to draw the meter leads on this side. I had my meter leads right here. Dryer's running, no heat, but now my meter says 0 volts. Okay, well the heater's not going to work if I don't have any electricity there, right? The first test we would make before we even did that, which I said yesterday, was to make sure that we have the 240 here or at the power source before we start taking panels off and start making a bunch of tests. We check to the machine and we have the proper voltage at the machine. The very next test you would make is where my meter leads are right now, and that would be what we did here on the diagram, here and here. If I have 240, my element is bad. If I don't have 240, and we discussed this the other day, any one of these controls could be bad, even the centrifugal switch. If one of them failed to operate, the heater will not work. So what we do is we leave one meter lead here, and I'm going to call it the red one, and the black meter lead is here. We say, oh, I got the machine running. I don't have any voltage to the heating element. Well, I know I had it at the plug. How come it didn't make it from here through this circuit to my heating element? How come I didn't make it there? So what I do is I do something called backtracking. You're going to hear this a lot in this industry. And it works the same for AC and other electrical circuits, backtracking. I give the statement is like, you're here, right? And your mom gives you $20 to go to the store and buy some milk and bread. Okay, you're here. This is the store. Okay, on your way to the store, you stopped at your girlfriend's house. Then you went to the park, shoot a few hoops. Then you stopped at the gas station. There's a friend of yours that's working there. You made one more stop at the pet store because you're thinking of getting a dog. By the time you got to the grocery store, you don't have that $20. You better find that 20 because mama gonna get you. But the point is that if you were here and you know you had the 20 here, to find that 20, what would you do? You would go back the path that you took to try to find that $20 bill. Where did you lose it? Okay? And we do the same thing when we're troubleshooting an electrical circuit. If I don't have the voltage here, I want to backtrack across the circuit and find out where is the voltage. By leaving one meter lead here, and then I go here the next test, I'm moving just one, the black one, and I say, oh, I don't have voltage. I don't have voltage. These are all the points I can test, like one side of the thermostat or the other side of the thermal cutoff. One side of the thermostat or the other side of the thermostat. So I'm just going back and back, no voltage, no voltage, no voltage. I'm here at the timer on red, no voltage, but when I go to the timer on black, all of a sudden it says 240. So I know line 1 made it to here. it never made it to here. And my problem is this switch. So what does that mean on the machine? Is if we follow each step back, I went to the high limit thermostat. So I moved my black meter lead from here to the high limit thermostat. I went to both sides of the high limit. One side coming out, one side coming in, no voltage. The next thing was the operating thermostat. So I went, my meter went off the page here. I went from one side of the thermostat, no voltage. Other side of the thermostat, no voltage. That would be this test, then this test. Okay? I still haven't found voltage. The next thing I'm going to go is to what? The thermal cutoff. So I'm going to move this meter lead here to one side of the cutoff. Then I go to the other side of the cutoff. Still no voltage here and here. So then I go to the red wire on my timer here, and now I'm here. My meter still says no voltage. I go like this, and I go to this one here, and all of a sudden I say I have voltage. The red one is always here on the meter the whole time. I've never even moved it. I'm just taking one lead, bam, 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 just testing one at a time, saying, where is that electricity? And I lost it here. Now, that same video where the guy made a mistake, you remember he tested black to red on the timer, and the timer was open. In that video I showed yesterday. And that would be the same way to find it, but he found it by testing ohms. I found it by testing voltage. Is there one better than the other? Anybody have any thoughts on that?
Voltage would probably be better than ohms, because with voltage
Go ahead.
with voltage you can go ahead and test. You can do the backtrack. You actually have current coming in, and you can find out what you get a reading for everything. You can find out what is coming in and what's going out. With ohms, a little bit different than that.
Yeah, I'd like to phrase it a little bit differently, though. Like, remember ohms, he had to pull a wire off of every part to make that test, the ohms test. So he didn't have a feedback, okay? But for voltage, we didn't disconnect any wires. But the tests that we make, believe it or not, we are testing the entire circuit when we are backtracking. We are not just testing the controls. What does that mean? Watch. I'm going to go back here and here on the heating element and do that same backtracking by moving the meter lead so you can see what I'm talking about. The dryer is running. I have no voltage here. When I move my meter lead here to here, what am I testing? I am checking for voltage, but what test is that going to... If I had 240 volts there, and I didn't have 240 here, so I have it here, and I move my meter lead here, I have voltage. I go over here, I don't have voltage. I'm going to go back here again. What am I actually testing?
You're testing components.
Okay, but what part or something has failed?
What's that, a high limit?
That's
No.
the high limit that I'm touching right now, but actually I'm not checking the high limit.
Oh, that's where the fault is in the circuit.
The fault is the wire between here and here. I have electricity here at the thermostat. If I followed it back, I would also have electricity here at the thermostat. Now, if the thermostat was at fault, electricity would be coming in, but then when I went to the other side, my meter would say no voltage. That would be the same as this switch. Look here. If I'm here and that switch is open, like you see it in the diagram, then I have no voltage at the switch. If I go to the other side of the switch, I have voltage. Can you see how this one would not give me voltage because it's open? Okay, but that's both sides of a switch. In this case, from here to here, there's no switch in between. It's just a piece of wire. So as I'm backtracking, watch. Here I start, no voltage. I move back to here, still no voltage, but I only backtracked across a wire. Now when I go here and backtrack, now I'm going across a thermostat. If the thermostat was fault, one side of the thermostat would give me voltage, and the other side of the thermostat would give me 0 volts if the thermostat was bad. And now I've checked the thermostat. I'm going to jump across the wire. I'm checking a wire. Now I'm checking the next thermostat. Now I'm checking a wire. Now I'm checking the thermal cutoff. I'm checking a wire. And now I'm checking a timer switch. So when we backtrack with voltage, different from what that guy did in the video yesterday, he did find the problem. The timer was bad. But if every one of those switches and thermostats all tested good, and the heater tested good, and you know you had power coming in, you could have a broken wire somewhere in the circuit.
Oh yeah, you said that one day.
It's not very common for wires to break or to fail, but by doing voltage tests, I'm testing all the wires and all the switches by backtracking that way. When I do an ohms test and I want to check out, let's say, the operating thermostat, I have to move both meter leads to that part to make the test. If I wanted to check that thermal cutoff, I had to move both meter leads to do that test. When I backtrack for voltage, I leave one here, and I only move one here, 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 here. I'm backtracking with one meter lead, trying to find the voltage. How far in this machine did the voltage come from this plug? And it made it from here to here on the black wire. But when my meter lead was on the red wire, I didn't have any voltage. So inside the timer, it wasn't letting the electricity get over there. I know that that's way far advanced, but I want you to hear it and think about it for a little bit, because we are going to slowly move into this troubleshooting. Because when you're working in the class, I'll be putting problems in machines. When you finish working on dryers in the class, before I move you on to other machines, I either give you a machine that came in that's broken and said, hey, Carl, go check out that dryer for me, tell me what's wrong with it. Or James, I got this washer here, I put a problem in it, see if you can find it. So you guys will have the opportunity as you get towards the completion of a specific appliance and have that opportunity to troubleshoot the problem, not just test the part and see if the part's good or bad. I want you guys to learn this process of troubleshooting. Again, I know it's a little foreign to you because you haven't had your hands on the machine. Some of you guys really haven't even used meters yet. And one thing is you have to learn to use your meter and have to learn to trust the reading that your meter is giving you when you're making a test. I've had people go to this element here and say, oops, I'm sorry, I didn't mean to move it like that, but say, I got 240, but my heater's still not working. Maybe I got a bad thermostat. How could the thermostat be bad? If it was bad, I wouldn't have 240 here. And the problem is my element. So when you guys are in the shop and the lab and you're doing these tests on these machines, I want you guys to learn to make a test and to know, should I have voltage here when it's working? Is that a good reading or not a good reading? And understand why. It is not the first thing you're going to do when you're working in the class, but it is something that is your end goal. When you graduate my class, one of the things I want you to be proficient in is to read this diagram, know where all these parts are on the machine, and then to know how to backtrack and find the fault.